All right, so welcome to everybody. I turned on the recording, so at this point you can type your name into the chat. We'll have a record for your attendance. This is the second to last session for this year, for this academic year. So next week is going to be the last session. So we'll have a little closing ceremony next week. Yeah, so I will have I think two good topics, a good topic for today and one for next week. And then we'll resume in the fall, in the late August or early September. And I think I have to spend a little bit of time thinking about what we're going to do next year. It's not just going to be a standard traditional, let's learn some math, because next year is the last year of the program. And so I want to do something that's maybe a little bit more active with the idea of getting the participants to be able to run, similar programs in Liberia after I'm no longer doing this. So I have to spend some time this summer thinking about how to get that to work. But I think it's going to be a little bit more active and people trying to, do some leadership, run their own sessions, et cetera, something like that. So it's not going to be the traditional thing that we've done for the last 4 years of me just teaching people some math. It's going to be more trying to prepare people to be able to run, similar workshops with other teachers who are interested. So I'm going to spend some time over the summer thinking about what's the best way to do that, and certainly in conjunction with the I help people in Liberia. So that's just a little bit of a heads up for what we're going to do next year. It's going to look different from the other from what we've been doing this year. Okay, but we still have today and next week, which will be standard classes for this year. So welcome once more to everybody. Thank you all for coming. I really appreciate it. And you can start typing your name into the chat so that I have your record for attendance. Okay. All right. So let me do a little bit of review from what we were talking about last time. So last time we were talking about sequences. Okay. So so we're talking about sequences. And so if you remember what a sequence is it's an infinite list of real numbers, not just a finite list, but a list that goes on infinitely. So you could have a sequence like 1, 2, 3, 4, 5. Or you could have a sequence like 1, 4, 9, 16, 25. And I write dot, dot, dot here to emphasize that the sequence goes on forever. So if I just say 1, 2, 3, 4, 5 with a period, technically that's not a sequence. Okay, so you need to have enough of a pattern so that the reader knows how to complete the pattern forever. So you know what the next numbers are going to be, 6, 7, 8, and so on. And the notation that we talked about last time is that these entries in a sequence generally are written as AN. So we call the first entry is called A1, the second one is A2, and then A3, A4, and so on. That's what we call the entries in the sequence. And the entire sequence, we use this notation, AN in some curly braces, or AN in some curly braces with an N equals 1 and infinity. That's just reminding you that you start at N equals 1 and you go all the way out to infinity. This is Stewart's notation. This is the notation in the Stewart book, the textbook that we have. But some other books, you'll see other notations. So sometimes you'll see AN in parentheses or AN from N equals 1 to infinity. There's lots of different notations that different books use. So I'm using this one because this is the book that I've given to you. And if you want to recall the chapter in the Stewart book, this is all in chapter, I'm trying to remember if it's 8.1 or 9.1. Let me look it up. This is in chapter 8.1 in Stewart's textbook. Okay. Okay, so this is what a sequence was. And we talked last week about two special kinds of sequences. So one kind was this called arithmetic sequence, and it was one where the difference between any two successive entries is constant. So the difference between any two successive entries is constant, right? And so what that means, and this constant is called the common difference. So we saw this example of an arithmetic sequence 2, 5, 8, 11, 14. We see the pattern in this sequence is that each number is 3 more than the previous number, right? So in this case, the common difference is equal to 3. And then the other kind of sequence that we saw was a geometric sequence, which is one where the ratio between any two successive entries is constant. And this constant is called the common ratio. So if you have a sequence like this over here, so 2, 6, 18, 54, 162, and so on, this is the example that we saw last time. You see that each entry in this sequence is 3 times the previous entry, right? So 2 times 3 is 6, 6 times 3 is 18, 18 times 3 is 54, and 54 times 3 is 162. So this is a geometric sequence, and the common ratio is equal to 3. Okay? So in this one, you add 3 each time. In this one, you multiply by 3 each time. Okay? And then we saw there's, lots and lots of sequences that are not arithmetic or geometric sequences. Arithmetic and geometric sequences are just two types that are particularly interesting. They appear a lot, and we'll see in particular the geometric sequences. We're going to see today a couple of applications of what they are. Okay. So this is the basics of sequences that we did last time. We didn't really say that much about sequences, but we define them and we show that there are these types of examples. Okay, and the key thing is arithmetic means constant difference, and geometric means constant ratio. And what you see is that a geometric sequence can grow much faster than an arithmetic sequence, right? These geometric sequence, we keep multiplying by 3, these numbers are going to get really big. 486 and then 1300 or 1400 and 1458 and so on. It gets big very quickly. Whereas the arithmetic sequences grow slowly, 2, 5, 8, 11, 14. Okay. All right. Okay, so now that we've reviewed this, we know we can do the first homework exercise. So the question is, if 18, 12, 8 is the beginning of a geometric sequence, then we want to write out the next 3 terms. Okay, so what would be the next 3 terms here? All right, so does anybody want to try this one?
Hello, Roberts.
Hello, yes, Abraham.
Yeah, the next three term will be 4.
So, okay, so
We
you're
have
saying the next 3 terms are 4.
4, 2,
Mm-hmm.
and 1.
Okay, so how do you get that? How do you get that answer?
Okay, using a formula for the geometric sequence, that's
Mm-hmm.
a Tn is equal to
Mm-hmm.
let's say Tn is equal to a
Yeah,
r raised to n minus 1.
right. So this is going to be what R to the n minus 1 is Tn, right? Or I
Yeah.
guess we called it An, but it's fine. You can call it whatever you want. Yeah.
Okay, yeah, okay.
Okay. It doesn't matter.
Okay. So
Right. So we want to solve for A and R, right?
yeah, to solve for a and r,
Right.
our a is the first thing that is 18.
Right. So A equals 18. That's the first entry.
Yes,
Mm-hmm.
the first answer. Then the second, let's say the R is the common ratio, that is the first 10.
Mm-hmm.
The common ratio is equal to the first 10 divided by the second, no, single.
Well, right. We gotta let's look at
Yep.
this, right? So A1 is A, and A2
Yeah.
is going to be AR, right?
Okay.
So if we want to solve
Okay.
for R, what do we get?
So for arrow, we say, okay, then arrow will be equal to A divided by,
Hmm.
arrow will be equal to A divided by A2.
Right. So, well, you got to put it up on the top, right? So
Yeah.
R,
Okay.
right, is AR divided by A, and we see AR is A2 and A is
Here is
A1, right? So this is going to be A2 divided by A1.
A1.
So yeah, so this is in general how you can get the common ratio. You take the second term and you divide by the first term. Or you could take the third term and divide by the second term. These should give you the same results if it's a geometric sequence. You can take any term and divide by the term before. That's going to give you the common ratio. Right. So in this case, what do we get? So we got 12 over
12 divided by
18.
It gives you
Hmm.
0.6666.
Right. So yeah. So let's keep it as fractions because that'll be a little easier. Great. So
Okay,
we're going
okay.
to keep it as two-thirds. Okay. So I'm going to write this as a question mark. Okay. So to get each next term, we need to multiply by two-thirds, right? So we start with 18, 12, 8. So then for the next term, we actually have to take 18 times two-thirds, right? Sorry, not 18 times two-thirds. We need 8 times two-thirds, right? So I think James wrote the answer here in the chat, right? So he claims the next three terms are 16 thirds, 32 ninths, and 64 27ths. And this is actually correct, right? Because what do you have? You have to multiply. So Abraham showed that the common ratio is two-thirds. So for each, to get the subsequent term, you have to multiply by two-thirds. So if we have 8 times two-thirds, we know by fractions that's 16 thirds, right? So we're going to get 16 thirds here. Then to get the next term, you need 16 thirds times two-thirds, right? And that's going to be 32 over 9. So 32 over 9 is next. And then lastly, you have to multiply again by two-thirds. So 32 over 9 times two-thirds is going to give you 64 over 27, right? So the next term is going to be 64 over 27. Maybe I'll write it. The way you get this is by multiplying by two-thirds, and then multiplying by two-thirds, and then multiplying by two-thirds. Okay, so this is the correct answer, actually.
Yeah, yeah,
Yes.
there.
Yeah, Abraham? Oh, Prince. Yeah.
Right. Yeah, our answer, if for any reason, our answer, the first beginning of this geometry sequence that we're given is everything is in whole number. So for every reason, let's take for instance, and then we'll simplify this into a decimal number. We'll also be wrong if we simplify to a decimal and then round it up to a whole number because the starting point is in whole number. So maybe
Yeah,
if we can get to fraction to be confusing.
yeah, I mean, so it is a little confusing. So the point is you should not round to a whole number here. If you want to leave it as a decimal, that's okay. But you don't want to round
Okay.
to a whole number. And basically, just because a sequence starts with whole numbers doesn't mean it's going to finish with whole numbers. Okay, so there's no reason that a sequence that starts with whole numbers has to finish with whole numbers. So especially when you have a geometric sequence where the common ratio is a fraction like this, then even if it starts with whole numbers, eventually it's always going to end up with fractions if your common ratio is a fraction. So that's part of why this question's a little confusing and why you're tempted to answer 4, 2, 1. It looks like they're getting smaller, and this is you divide by 2, divide by 2, divide by 2. But actually, if it's a geometric sequence, you really have to keep the ratio constant. And so that's going to mean you're going to have 16 thirds, 32 ninths, and 64 27ths. And it's usually the best to just leave it as a fraction.
Okay, thank you. Another question, sir.
Yep.
Yeah, okay. If the geometric sequence starts with a positive number as it is it also possible that if anything is requested for to result into a negative number as well?
Yeah, yeah. It can be negative. The geometric sequence can have all of the numbers negative, or it can alternate positive and negative. So, for instance, here's a geometric sequence. If I have -1, 2, -4, 8, -16, and so on. This is a geometric sequence because the common ratio is -2, right? For me to get one from the other one, I'm always multiplying by -2, right? This is multiplying by -2, multiplying by -2, multiplying by, sorry, multiplying by -2, and then again multiplying by -2. Yeah. So you can have negative numbers, positive numbers, fractions, irrational numbers, anything. The only thing that matters for a geometric sequence is that the ratio is constant, is that you have a common ratio. Every term is gotten by the same multiplication. You have that, then you can have positive, negative, anything you want.
Okay, thank you so much.
All right, you're welcome. Okay. Other questions here? Okay. All right. So let's keep going. Okay. So homework exercise 2. Can a sequence beginning 2, 4, 6 be a geometric sequence? So can you have a geometric sequence that starts with 2, 4, 6?
Yeah,
Is
I
that all
think you're
right?
asking a
Yeah.
question, right, sir?
Yeah, Prince.
Yeah, sir, I think you're asking a question. That is a question asked, right?
Yeah, this is a
So
question. So
for
yes
me,
or
yeah,
no,
for
right?
me, I believe that it's not a geometric sequence.
Right. So Prince says no. So why not?
Yeah, what I'm looking at this because if we find the common ratio for this number 246, the common ratio will not be, given into what we call in a geometric sequence, which the ratio doesn't change. But yeah, if we look at arithmetic and we're taking the ratio to find the common difference, it will get the common difference in the arithmetic series or sequence.
Right. So you're actually right. This is actually an arithmetic sequence, but we don't even need to show that. We just need to show that it's not geometric, right? So, right. So what happens when we try to do the common ratio here? Well, I can look at 4 divided by 2. Well, that's 2. And then I can look at 6 divided by 4. It's the next two terms, right? That's 1.5. And these two things are not equal. Right? And so this means, right, that we don't have a common ratio, right? We don't have a common ratio because we evaluate the ratio 4 to 2 and we get one answer, and we evaluate the ratio 6 to 4 and we get a different answer. And so it means it's not common. It's just two different ratios. It's not a common ratio. Okay? So that means this is not a geometric sequence. And as Prince said, in fact, this is an arithmetic sequence with common difference 2, right? Because we do, in fact, get each element by adding 2 to the next one. So we can start with that this is an arithmetic sequence with common difference 2, but it's not a geometric sequence. Okay? Any questions? Right. It's not that the consecutive terms are not constant, it's that the ratio between the consecutive terms is not constant. Here we have one ratio between these two terms, that's 2, and here we have another ratio between these two terms, that's 1.5. And because these things are not equal, that means that ratio is not constant. Any questions?
But
Yes, James?
it is possible to create a function from a geometric sequence.
A function for a geometric sequence?
Yeah.
Yeah, I mean, so a formula, right? So maybe I should have stated this back at the beginning, right? So the formula for a geometric sequence, if you want a formula, and Abraham mentioned this, the formula is that the nth entry in a geometric sequence is given by a times r to the n minus 1, where here a is the first entry, and here this r here is the common ratio. Okay, so this is the formula that we did last time for the entries of a geometric sequence. It's the first entry times the common ratio raised to the n minus 1. And it turns out that this formula doesn't fit the sequence 2, 4, 6. There's no way that you can choose A and R that punching in n equals 1 gives you 2, and n equals 2 gives you 4, and n equals 4 gives you 6. There's just no way to do that, and that's because they don't have a common ratio. Does that answer your question?
Yes. Yes.
Okay, great. Other questions? Okay. Okay. All right. So let's move on. So let me also recall one other thing from last week. So we talked about the limit of a sequence. What does it mean that the sequence has a limit L? Well, it means that if you take n large enough, you take n sufficiently large, that's enough to get the terms of the sequence, the ANs, arbitrarily close to L. So it's saying that your sequence gets closer and closer to L and gets as close as you want by taking n large enough. And the notation that we use is the limit as n approaches infinity if an is equal to L. Okay? And then we had this theorem last time that if an was a sequence and if f of x was a function, that when you plug in integers, you just get the entries of the sequence for each natural number n, then if the limit of the function is L, the limit of the sequence is also L. So this is maybe a lot of words, so let me just recall the example that we did last time. Let's say that we have a sequence given by an equals 1 minus 1 over n. This is a sequence. And we want to know what is the limit as n goes to infinity of an. Well, what we do is we consider the function f of x equals 1 minus 1 over x, right? This is the same function as the sequence that we had before, right? So we just change the n to an x. And so what I should do is I'm going to observe that if I punch in an integer for this function, this is just 1 over 1 minus n, and that's the same thing as an. Okay? So if I have this function, well, we know that the limit as x goes to infinity of 1 minus 1 over x is equal to 1. This is the kind of limit we've done earlier in the term, right? This term goes to 0, and then the 1 stays at 1, right? The 1 over x goes to 0, and the 1 still goes to 1. So we get 1. And since we know that, what the theorem says is that we conclude that, in fact, the limit as n goes to infinity of 1 minus 1 over n is also equal to 1. Okay, so you can evaluate the limit of a sequence just by doing the same limit of the function that corresponds to the sequence. And that's just the function where you use an x instead of the n. Okay. All right, so this is a theorem that we did last time. So the way that you calculate a limit of a sequence, usually you can just calculate the limit of the function that that gives you the values of the sequence. And if the limit of the function works, then the limit of the sequence also works. Okay, So that's usually how we do a limit of a sequence. So after recalling that, let's look at homework exercise 3. So homework exercise 3 says it's two parts. So we first have a sequence where an is going to be defined as sine of pi times n. And the first question says calculate the limit as n goes to infinity of an. So maybe let's do this part first before we even read the next part of the question. Right? So we want to calculate limit as n goes to infinity of an. Okay. So the question is, what can we do with this? All right. Well, what are these things? So what is this sequence? Well, A1 is sine of pi. A2 is sine of 2 pi, right? This is the definition of the sequence. A3 is sine of 3 pi. And A4 is sine of 4 pi, and so on. So for this, we have to remember a little bit of trigonometry. So do we remember what sine of pi is on the sine curve? Remember, the sine curve looks like this. It goes up and down and up and down. And this is 0. This is pi. This is 2 pi. And this is 3 pi over here. So what does it look like all of the entries in this sequence are equal to, right? This is the graph of y equals sine x.
That Robert?
Yep.
That's the sine of pi. A pi there will be representing 90 degree, and sine of 90 degree is equal to 1.
Be careful, remember, pi isn't 90 degrees. Pi is 180 degrees, right? Remember, pi radians equals 180 degrees. So we have to look at sine of 180 degrees. Remember what that means. We draw this unit circle, and you follow this 180 degrees from the x-axis all the way over. 180 degrees is half the circle, right? And so the coordinates of this point here, remember, cosine is defined as the x-coordinate, and sine is defined as the y-coordinate. So what's the y-coordinate of this point over here? When you go halfway around the circle, that's pi radians, or 180 degrees. Right, I mean, another way of saying this is sine of 180 degrees, then, so if A1 is sine of 180 degrees, A2 is sine of 360 degrees, A3 is going to be sine of 540 degrees, and A4 is going to be sine of 720 degrees. Okay. So what is the value of all of these sines? Remember, sine is the y-coordinate when you go around the circle 180 degrees, then 360 degrees, then 540 degrees, 720 degrees, and so on. You keep going around, going around, going around, and going around. So maybe just the first one. What about 180 degrees? What do we get with sine of pi, or sine of 180 degrees? What's the y-coordinate here? I mean, we can just look at the graph, right? Y-coordinate's 0 here, right? You're on the x-axis, right? So, or you can look at the graph of y equals sine of x, and you see it crosses the x-axis at pi, at 2 pi, and at 3 pi, right? So it goes through 0, and then through 0, and then through 0 again, right? So it hits 0 at all of these points. So that means that all of these values of sine of some integer times pi are all 0. A1 is 0, A2 is 0, A3 is 0, A4 is 0, and so on. Right? Because at any multiple of pi, sine goes to 0. Because we do pi is a half circle, y coordinate 0. 2 pi is another half circle, y coordinate 0. 3 pi is another half circle, y coordinate 0. 4 pi, another half circle, y coordinate 0. 5 pi, another half circle, y coordinate 0, and so on. Right? So no matter how many multiples of pi you take, sine of that is always going to be 0 because sine represents the y coordinate on the unit circle. Or if you don't like the unit circle, you can remember the sine wave graph. And you see that this makes a wave every pi. So it takes pi to come back to the x-axis, another pi to do this, another pi to do this, and so on. Okay? So if we look at this sequence of an, this is the same thing as the limit as n goes to infinity of the sequence 0, 0, 0, 0, 0, etc. So this is just a sequence where every single entry is a 0. Okay? If every single entry is a 0, that means the limit is 0, right? It's just the 0 function. Okay, so every single entry is 0. Okay, so the limit of the sequence is 0. Before we move on to the second part of the question, are there any questions about the limit of this sequence being 0? Okay, so let's look at the second question. So we note that if we take the limit as x approaches infinity of sine pi x, right? I mean, if this is y equals sine x, then sine pi x is the same wave, it just waves a little faster. So this limit does not exist since the function oscillates, right? If I take y equals sine of pi x, the graph actually just looks like this. It's the same as a sine curve, but instead of fluctuating every pi, it fluctuates every 1. So this is 1, 2, 3, 4, 5, 6. This is the graph of y equals sine pi x. And certainly, the limit as x goes to infinity of sine pi x doesn't exist because this is an oscillating function. So it has no limit when you go to infinity. So the question is, why does this not contradict the theorem on the previous slide? So the theorem on the previous slide said the limit of the sequence is the limit of the function. But here, the limit of the sequence is 0, and the limit of the function does not exist, right? So limit as n goes to infinity of, as x goes to infinity of sine of pi x, this does not exist. So I thought the theorem said the limits are supposed to be the same, but now, in this example, the limits are different. One is 0, and one does not exist. So the question is, what gives? Why is this not a contradiction? And the answer is, let's read the theorem carefully. Right? So the theorem says, if the limit exists, if the limit is equal to L of the function, then the limit of the sequence is also equal to L. It doesn't say it the other way around. It's an if-then statement. This is an asymmetric statement. That's telling you that if one thing is true, then the next thing needs to be true. But what are we saying here? Here, the limit of the function does not exist. So if the limit of the function doesn't exist, then this theorem doesn't tell you anything. Right? L is a real number. So we're saying that if the limit of the function is some real number, then the limit of the sequence has to be some real number. If the limit of the function doesn't exist, then this theorem just doesn't tell you anything. Okay? So it's not a contradiction because this theorem is not making any claims if the function limit doesn't exist. It might be possible that the function limit doesn't exist, but the sequence limit still does exist. That's the case in particular that's the case when we use this example. The function limit doesn't exist, but the sequence limit does exist. And that is completely fine by the theorem. The theorem's just saying that if the function limit does exist, and if it's L, then the sequence limit has to exist and also be L. Okay, so that's fine. That's a true theorem. But if this function limit doesn't exist, then this theorem just doesn't tell you anything. It's not a contradiction. It just doesn't tell you what's going on. Okay, so that's why it's not a contradiction, because if the function limit doesn't exist, then theorem's not claiming anything. Okay, so we needed a different way to evaluate this limit of the sequence. And the way that we could do that was just by writing down the sequence and seeing, oh, look, actually every single entry in this sequence is a 0. So that means that the limit has to be 0. All right, any questions? Okay. All right, so let's move on. So today I want to talk about series. This is our new topic, which is in particular what happens when you add together everything in a sequence. So by the way, if you want to look at the book, this is going to be chapter 8.2 of Stewart. Okay, so we all know how to add together finitely many numbers, right? If I give you 1 plus 2 plus 3 plus 4 plus 5, you know what that means. It's 15 when you add them all together. Okay? So no problem. And maybe if it's a lot of numbers, it might take you a long time, but there's no question with how you do it. You know how to add two numbers, which means you know how to add 100 numbers. You just have to do them one at a time, and at some point you finish. So now what's a series in math? A series is an infinite sum. Okay, so a series is an infinite sum, meaning you're adding up the sum of all of the entries in a sequence. So you're adding up infinitely many numbers. And I should note that some of the entries that you're going to add, they're allowed to be negative. So if you have some pluses and some minuses, that's fine in a series. So if you had, 1 minus 2 plus 3 minus 4 plus 5 and so on, that's fine. That's still a series. The numbers you're adding in that case would just be 1 and minus 2 and 3 and minus 4 and 5 and so on. Okay. Okay. So a series is an infinite sum. You add everything up in this series. So there's a few ways of writing this. So if you have a sequence, you can use what's called summation notation to write the series. So that's the sum from n equals 1. Since it's a series, we go out to infinity. So it's the sum from n equals 1 to infinity of an. This is what's called summation notation. Okay, summation notation. Okay, so this is the associated series. Okay, so the series, we write it as the sum from n equals 1 to infinity of an. This just means taking a1 plus a2 plus a3 plus a4 and so on out to infinity. It means you add up all of the terms of the series. So we can write this out. So if I write 1 plus 2 plus 3 plus 4 plus 5 plus dot, 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 or 1/2 plus 1/4 plus 1/8 plus 1/16 plus dot, 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 both of these are series. Right? The difference between a series and a sequence is just a list, whereas a series is a sum. You're adding up all of these numbers. And if we wanted to write this in summation notation, the first one could be written the sum from n equals 1 to infinity of just n, right? Because n equals 1 gives you 1, n equals 2 gives you 2, n equals 3 gives you 3, and so on. So that's 1 plus 2 plus 3 plus 4 plus 5. And then this other one, 1/2 plus 1/4 plus 1/8 plus 1/16, you could write this as the sum from n equals 1 to infinity of 1 over 2 to the n, right? Because 1/2 is 1 over 2 to the 1, 1/4 is 1 over 2 to the 2, 1/8 is 1 over 2 to the 3, 1/16 is 1 over 2 to the 4, and so on. So each successive term here is you're doubling the denominator. Okay, so these series can be written. So this is how you would write the series in a compact notation with a formula, but usually it's also good enough to just write out some number of terms until the pattern is clear. So the pattern here is very clear. You're adding 1 with each new entry, and the pattern here is very clear. Each new entry is half of the previous one. Sorry. Okay, so any questions about what a series is? We're just adding up the elements of a sequence. And I haven't told you how to do this yet. I'm just telling you when you see a bunch of numbers going on forever with pluses between them or pluses and minuses, that means that you have a series. Okay, any questions? Okay. All right, so let's move on. So, okay, what's a partial sum? So when we want to know, the goal is to kind of try to figure out how to sum up a series. How do you add infinitely many numbers, right? We know how to add finitely many numbers. We want to know how to add infinitely many numbers. Well, okay. Well, suppose we have a series. So I'm going to declare the kth partial sum of the series to be the sum of the first k entries in the series. So a1 plus a2 plus a3 all the way up to ak. And as a notation, we use sk to represent the kth partial sum of the series. So you should think of the s as being for sum. So this is, this represents a sum. So sk means we take a1 plus a2 up all the way up through ak. So if we have a series like this, 1, 2, 3, 4, 5, what are the partial sums? Well, S1 is just the first term. It's the sum of the first 1 terms, which is the first term, which is 1. S2 is the sum of the first 2 terms, so that's A1 plus A2. So that's 1 plus 2, that's equal to 3. S3 is the sum of the first 3 terms, so that's A1 plus A2 plus A3, which is 1 plus 2 plus 3, which is 6. S4 is A1 plus A2 plus A3 plus A4. That's 1 plus 2 plus 3 plus 4. That's 10. And I'll do one more. So S5 is equal to A1 plus A2 plus A3 plus A4 plus A5, which is 1 plus 2 plus 3 plus 4 plus 5, and that's equal to 15. Okay, so these are the partial sums. So the first partial sum is 1, the next one is 3, the next one is 6, the next one is 10, and the next one is 15. We're just adding up more and more entries in the series. And these, by the way, if you've seen these numbers, 1, 3, 6, 10, 13, 15, these are sometimes called triangular numbers. And these are called triangular numbers. And the reason is if you look at like a triangle like this, I'm going to just draw a kind of block triangle like this. If you see, the first row is 1, the second row has 2 squares, the third row has 3 squares, the fourth row is 4 squares, the fifth row is 5 squares. When you put them all together, it looks like a triangle. And each successive triangular number tells you how many squares are in the first n rows. So 1 is the number of squares in the top row. 3 is the number of squares in the first 2 rows. 6 is the number of squares in the first 3 rows. 10 is the number of squares in the first 4 rows, and 15 is the number of squares in the first 5 rows. So that's why these are called triangular numbers, because they measure the number of squares in a triangle like this. Okay.
Yes, sir.
Yes,
Yes,
Prince.
sir.
Yeah.
Yeah, thank you so much. Thank you so much for this. I want to ask a question as to
Hmm?
whether the Pascal triangle is also available to be used into the partial sum. If we can use the Pascal triangle as also.
Yes, so these numbers happen to be in Pascal's triangle, right? So for those who don't know Pascal's triangle, you start with ones down the side, and then in the middle, each number is the sum of the two previous numbers. So you get like 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, and I'll do one more row, 1, 6, 15, 20, 15, 6, 1. Sorry that it's written so small, but this is the so-called Pascal triangle. And if you look at these partial sums over here, you see that they show up on this diagonal in Pascal's triangle. Um, you get 1, 3, 6, 10, 15. And in fact, the next one is going to be 21, and so on. So, yeah, you can recognize these partial sums in Pascal's triangle, but that's a very special property of this series. Okay, so if I gave you some other series, it might not have anything to do with Pascal's triangle. But that was good intuition that these numbers, these triangular numbers here, you really do see them in Pascal's triangle. You recognize this pattern. The next one is going to be 21 because you're going to add 6, and that's going to be exactly what shows up next in the diagonal here. So yeah, so these partial sums appear in Pascal's triangle, but that's because of this specific series. For another series, it might not appear.
Okay, thank you so much.
Okay, you're welcome. Other questions? Okay. All right. Okay, so these are partial sums. So if you have a series, the series might be complicated. Adding up infinitely many things is hard. I haven't told you how to do it, but partial sums are easy, right? Partial sums is just take the sum of the first k numbers. So it's easy to compute partial sums. You just need to do addition, and this gives you partial sums. Okay. So what do we do for an actual series? So this is where the kind of calculus comes in, because we're going to be talking about limits and infinite things. So what does this have to do with calculus, right? Well, on the previous slide, we talked about partial sums. So what should we do to define the total sum of a series? Well, remember, this SK was what we called the kth partial sum. That was the sum of the first k terms. And so as k gets bigger and bigger, this sum includes more and more terms of the series, right? If I take the 100th partial sum, that's going to have the first 100 terms. If I take the 1000th partial sum, that's going to have the first 1000 terms. I can take the first million terms, the first billion terms, right? I can take these partial sums as big as I want, and it's going to have lots and lots of terms. And so, but of course, no partial sum has all the terms because there's infinitely many, right? So I can take more and more terms, but no partial sum is going to have all the terms because for every partial sum, I have to stop somewhere. So what do we do? Well, this is calculus. Everything in calculus is based on limits. So what we do is if we want to include all the terms, what we do is we take the limit as k goes to infinity. So what we do is in particular, take the limit as k goes to infinity of the kth partial sum. Okay. And if you do that, then that's kind of including all of the elements in the series, right? You're adding up all of them all the way out to infinity. That's what happens when you do the limit. So let me give you the definition formally. Let's say that we have a series, sum from n equals 1 to infinity of a(n). So it's just a1 plus a2 plus a3. And let's say these are the partial sums. The partial sums are given by sk. So if the limit as k goes to infinity of sk exists, and if it equals L, then we say that the series converges to L, and we say that the sum of this infinite set of numbers is equal to L. So basically, what is the sum of an infinite set? It's the limit of the sum of the finite sets. So it's you add up the first three, then the first four, then the first five, then the first six, and so on. And if that has a limit as you go to infinity, then that should be the sum of all of the entries. And if the limit does not exist, then you're out of luck. Then you can't add up all of the entries in the series, and we just say that the series diverges. Okay? So series converges means you can add up all of the elements. Series diverges means you can't. Okay, and some series are going to converge and some series are going to diverge. Okay? Some are going to converge and some are going to diverge. Okay, and so unlike with finite sets of numbers, you can always add up finitely many numbers. Well, sometimes you can add up infinitely many numbers and sometimes you can't. Okay? So we're going to have to see whether or not we can add up infinitely many numbers. Sometimes we can do it, sometimes we can't. So the definition may seem a little bit complicated. So let's try to do this in some examples so that it'll be clearer. Okay? So first, we're going to look at this series, 1 plus 2 plus 3 plus 4 plus 5. I'm going to claim that it diverges, right? So remember, we've already calculated some of these partial sums on the earlier slide, right? So partial sums, we already calculated S1 equals 1, S2 equals 3, S3 equals 6, S4 equals 10, S5 equals 15. We can do some more, right? S6 is 1 plus 2 plus 3 plus 4 plus 5 plus 6. Another way of saying that is it's S5 plus 6, right? Because the first 5 here is S5. That's S5 plus 6, which is 15 plus 6, which is 21. Maybe I'll do one more. S7, for the same reason, is going to be S6 plus 7, right? That's 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, where here is S6. And if you add all of these numbers up, this turns out to be 28. And so it turns out that the sequence of partial sums is 1, 3, 6, 10, 15, 21, 28. To get the next partial sum, we're going to add 8. So that's going to give us 36. Then we're going to add 9. That's going to give us 45. Then we'll add 10. That'll give us 55. Then add 11 for 66. Add 12 for 78, and so on. So what you see is that this sequence of partial sums is just getting bigger and bigger, right? So does it have a limit? Not really, right? I mean, you could say the limit is infinity if you want, but the limit is not some finite number. So the limit of this sequence you can say that the limit of this sequence does not exist. Or you could say that the limit of the sequence equals infinity. Okay, either one is okay. But the point is that this does not really have a limit, right? These things are growing without bound. They're going off to infinity, which means that you can't say the sum of 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 and so on up to infinity is the best you can say is that it's just infinity, okay? Or you can say the sum doesn't exist, the sum diverges. And the reason is because if I look at these partial sums, I take the sequence, and the sequence of partial sums does not converge. It does not have a limit. Okay? So if the sequence of partial sums doesn't have a limit, that means that there's no way to define the limit of the series. Okay, you just can't say that it exists. Okay, so I'll say, so the series diverges. A limit sequence doesn't exist, which means the series diverges. Okay? All right. And you just write down the partial sums, and you just see that they're growing without bound. There's really nothing to say. Definitely no limit. All right. Any questions here for this example? Okay, so sometimes you try to add up infinitely many numbers and it just doesn't work. If the numbers are getting bigger and bigger, it's not going to work, right? But sometimes you can add up infinitely many numbers and it does work. So let's look at the next example. Next example says, we'll do this other series. We're going to evaluate the sum from n equals 1 to infinity of 1 over 2 to the n. That's 1/2 plus 1/4 plus 1/8 plus 1/16, and so on. So what do we have to do? We have to look at the partial sums. Okay, well, the partial sum S1 is just the first term. That's 1/2. The second partial sum is A1 plus A2. That's 1/2 plus 1/4, and that's equal to 3/4. Third partial sum, that's the sum of the first three terms, A1 plus A2 plus A3. That's 1/2 plus 1/4 plus 1/8. We can write that as 3/4 plus 1/8. And if you do your fractions, this turns out to be 7/8. Let's do one more. S4 is equal to A1 plus A2 plus A3 plus A4. Well, that's 1/2 plus 1/4 plus 1/8. The next term, A4, each term is half the previous one, so it's going to be plus 1/16. And you already know that this over here is 7/8. We've already done that. So this is going to be equal to 7/8 plus 1/16. And if you write this down, this is going to be 15 over 16. Okay. So we're starting to see a pattern here, right? So it turns out that the sequence of partial sums is, well, the first partial sum's 1/2, then 3/4, then 7/8, then 15/16. Turns out the next one's going to be 31 over 32, and then 63 over 64, and then 127 over 128, and so on. So looking at this sequence I claim does have a limit. What does it look like the limit of this sequence should be? What are these numbers approaching?
Yeah. Can we say 1?
1, exactly, yes. So Armstrong has the right answer. So the limit is 1. Because look at all these. They're approaching 1. This is 1 minus a half. This is 1 minus a quarter. This is 1 minus an eighth. And then this is 1 minus a 16th, 1 minus a 32nd, 1 minus a 64th, 1 minus a 128th. So it's 1 minus teeny tiny numbers. They're getting smaller and smaller. And so in the limit of this sequence is just going to be 1. So what we say, since the partial sums go to 1, this is what's happening as you add more and more terms. So in the limit, it's like you're adding all the terms. And so the limit of this infinite series is 1. So what we can say is the sum of these infinitely many numbers, 1/2 plus 1/4 plus 1/8 plus 1/16, etc., this is equal to 1. Okay? So in other words, you could say the series converges to 1. Okay. All right. Any questions on this? Okay. So this first series here, you can't add. It diverges because these partial sums go to infinity. But the second series you can add because these partial sums just go to 1. Even though you're adding more and more elements, in the end, your answer is just 1. Okay. All right. So let me say something you may have heard of. So this is called Zeno's paradox. This is a very classical paradox from 2,000 years ago. So the Greek philosopher, that should say Zeno. So propose the following paradox. So suppose you're trying to walk from point A to point B. So first you have to walk halfway there. Then you have to walk half of the remaining distance. Then half of the remaining distance after that, and so on forever. And how can you ever reach point B if you have to complete an infinite sequence of walks to get there? Right? So imagine you're here. This is you at point A. And you're trying to get over here to point B. Okay. So how do you walk to point B, right? Well, first you've got to go halfway, right? So we think of this as maybe being one half. Got to go halfway. Then you've got to go halfway to point B, right? So I'll put this over here. That's another it's halfway from the halfway point, which is kind of a quarter of the way, right? Then you need to go halfway from here to point B. I'll put it in another, you have to go to the halfway point over here, so that's going to be 1/8. Then maybe you have to go halfway again. So halfway over here, you're doing 1/16, and so on, right? So in order to get from point A to point B, you've got to keep going. You got to go halfway, then you've got to go halfway again, then halfway again, then halfway again, then halfway again. And how can you ever get there if you have to do infinitely many things, right? Because you just have to keep going halfway. And so you're never going to get there, right? So Zeno was like, I mean, well, obviously you can get from point A to point B, but isn't it weird to think about how that can happen? Because you have to do infinitely many things to just do a simple walk from point A to point B. And the answer, or an answer, is kind of here in this infinite series. The point is, we showed that 1/2 plus 1/4 plus 1/8 plus 1/16, and so on, that this is equal to 1. So it turns out that adding up these infinitely many distances, adding up this infinitely many distances, is still gives you something finite, right? So you should think this is how it works. You know, you're adding up infinitely many things. And then you still get a finite answer. Okay? And this is part of what makes Zeno's paradox not really a paradox. You can get from point A to point B, even if you have to do infinitely many things, because even doing infinitely many of them, you end up with a finite sum. You end up just going a finite distance. So you can do these infinitely many things in a finite amount of time. Okay, so this is one of these thought experiments that the Greek philosophers like to do, and seem like you can't get from point A to point B because you have to do infinitely many things, but it's okay because this infinite sum still gives you something finite, so you can still do it.
Yeah, I have a simple question,
Yeah,
please,
Prince.
sir. Yeah, okay. Is it only possible that if I work on a distance to just be on half of the distance I want to cover, will it always be possible that I have to start with a half or to be on half of the distance?
No, I mean, you can start with whatever you want. This is just one way of thinking about how you would walk the whole way. You can say, well, you'll stop when you're halfway there, and then stop when you're again halfway there, and then stop when you're again halfway there. And if you keep doing that, then you can never get there, right? So somehow the key is not to stop. Like some camera can take a picture of you while you're halfway to all of these places, but those time intervals are going to get smaller and smaller, and they're going to add up to just a finite amount of time. So in a finite amount of time, you can reach point B, as we all know, because we know that you can walk from point A to point B. So there's got to be some way to do it. So this objection is not
Yeah,
valid.
okay, so that's what I'm
Yeah,
saying. So exactly, if I want you to start from point A and then walk and then go straight to point B, that's
right,
what I'm saying. Not to just be stopping at half and then walk straight to go to point B.
right.
It's possible.
Exactly. If you have to stop every halfway, then you'll never get there. But the point is, if you don't stop, then you do these infinitely many little intervals in finite time because they all add up to just a finite distance.
Oh,
And
okay.
that's what we're doing.
Oh, thank you.
Okay, you're welcome. So if you want to look this up, you can read this on Wikipedia. You can read an article about Zeno's paradox. they'll say a little bit more about this. Okay, any questions
Yeah,
here?
so again,
Yeah,
if we look at the paradox here, I think a paradox are if I'm saying because it's a statements that suggest, but it's the contradiction, but it's actually talking about truth. Yeah, I think about
exactly.
paradox.
Yeah. Hmm.
Yeah, so if that means that the contradiction is what they're talking, maybe they're taking the half part of odd, taking the full, distance to go, but still you will say reach to the true fullness of where you are going to or where you're going to.
Yeah, so the paradox, the contradiction is that you can't ever walk from somewhere to somewhere else because you have to do infinitely many things to get there. That's what seems like is the contradiction, that you can't ever walk from somewhere to somewhere else. But of course you can. So there has to be some resolution. And the
Mm.
resolution is this whole that the sum of an infinite series can be something finite.
All right, thank you so much.
Okay, you're welcome. All right, other questions? Okay. So we'll see another thing like this. Okay. So this is a geometric series, right? Because each geometric series just means it comes from a geometric sequence, right? And each one is half the previous one, right? So if we do this, this is actually a geometric series with common ratio 1/2, right? Yeah. So this is geometric series with common ratio 1/2, right? Each term is half of the previous one. Multiply by 1/2, multiply by 1/2, multiply by 1/2. Okay. So it turns out that you can sum up any geometric series within reason. So remember that the nth entry in a geometric sequence we saw already. This is an, which is a times r to the n minus 1, where a is the first entry and r is the common ratio. So now let's say that we add all of this up to get a geometric series. So how do we evaluate the sum of this series? Well, we have to do the partial sums, right? So the partial sums, well, S1 is just going to be A, right? Because that's the first entry. S1 is A1, which is A. S2 is A1 plus A2, which is A times 1 plus R. Well, let me add an extra step. That's A plus AR, which is A times 1 plus R. S3 is A1 plus A2 plus A3, which is A plus AR plus AR squared. Or in other words, A times 1 plus R squared, if I pull out an A, right? And we see the pattern. We see the pattern that Sn or Sk is going to be A1 plus R squared all the way up to R to the K minus 1. Okay. So the question is, what is the limit as K goes to infinity of Sk? Right? This is going to be the sum of the series. If you're trying to add up a geometric series, sum of the geometric series, we have to figure out what's the limit of these partial sums. Okay. So let me tell you what you can do. We'll need a new page for this. So remember, what's our problem? Is to calculate the limit as K goes to infinity of A times 1 plus R all the way up to R to the K minus 1. Okay. Well, here's a trick. So a trick is if you take 1 plus R all the way up to R to the K plus 1 and you multiply it by 1 minus R, well, what is this? Well, this is just distributive law. It's this whole thing times 1 minus this whole thing times R, right? So that's 1 plus R up to R to the K plus 1, and then minus R times 1 plus R plus up to R to the K minus 1. Or if I simplify this, it's 1 plus r plus all the way up to r to the k minus plus 1. Sorry, it's k minus 1. Sorry, these should be k minus 1s. This should be r to the k minus 1. This should be r to the k minus 1. So r to the k minus 1 minus, and now we can multiply through this r. So that's r plus r squared plus all the way up to r to the k. And now what you see is you get a lot of cancellation, right? Here you have r squared, all the way up to r to the k minus 1. And here you have r squared, all the way up to r to the k minus 1. Maybe I'll write down one extra term. I'll write r to the k minus 1 and then r to the k. And so what happens here is that you get this cancellation. All of these terms here cancel out with all of these terms here. And what you're left with is just 1 minus r to the k. Okay, so if you write 1 minus r to the k plus 1 times, sorry, 1 plus r plus all the way up to r to the k plus 1, and you multiply it by 1 minus r, you end up with 1 minus r to the k. So in other words, you get that 1 plus r plus all the way up to r to the k plus minus 1. This is equal to 1 minus r to the k over 1 minus r, right? Because I'm just dividing both sides by 1 minus r. If I have this and I divide by 1 minus r, then that's the same as this dividing by 1 minus r. Okay. So what were we trying to calculate? We wanted to calculate a times all this. So a times 1 plus r plus all the way up to r to the k minus 1 is equal to a times 1 minus r to the k over 1 minus r. Okay, just multiply both sides by a. Right, and this is our partial sum. Remember, this is our sum sk. This is what you get when you add the first k elements of a geometric sequence. Okay. So we want to know what happens as k goes to infinity. So what happens as k goes to infinity? Well, let's look at this term here. What happens to r to the k as k goes to infinity? Well, if r is big, this term gets big, and everything diverges. But it turns out that, well, if the absolute value of r is less than 1, so if r is between 0 and 1 or between minus 1 and 0, so if r is small, then when you raise it to very high powers, it gets even smaller and it ends up going to 0. So if this is true, then the limit as k goes to infinity of r to the k actually is equal to 0. So if the absolute value of r is less than 1, then the limit as k goes to infinity of r to the k equals 0, right? If r is like a half, then you keep raising it to higher and higher powers, it's going to go to 0. It becomes a fourth, an eighth, a 16th, a 32nd, and so on. It turns out for any number smaller than 1, if you raise it to big, big, big powers, you end up getting 0. And so that means that the limit as k goes to infinity of sk, which is the limit as k goes to infinity of a times 1 minus r to the k over 1 minus r, well, if this piece over here just goes to 0, this just becomes a times 1 over 1 minus r, or simplified, a over 1 minus r. Okay, so you end up with this very clean formula. All right, so if you have a geometric series with initial term a and common ratio r, then the sum of that geometric series, that's the limit of the partial sums, as long as the common ratio is less than 1. You need the common ratio to be less than 1. But as long as the absolute value of the common ratio is less than 1, you end up with this very clean formula. You end up just getting a divided by 1 minus r. So maybe that's important enough that I'll say it on another page. So the summary If the sum from n equals 1 to infinity of an is a geometric series with first element, the a1 is a, and common ratio r, with we need this assumption that the absolute value of r has to be less than 1. Then the sum of the geometric series is given by this very simple formula, a over 1 minus r. And an example of this, which we've seen what do you do if you have 1/2 plus 1/4 plus 1/8 plus 1/16, and so on. Well, in this case, a is the first term. That's 1/2. Common ratio is also 1/2, right? Because each term is 1/2 of the previous one. So that means the sum is equal to a over 1 minus r, which is 1/2 divided by 1 minus 1/2. 1 minus a half is just a half, so that's a half divided by a half, and that's just 1, just like we already saw. Okay, so the sum of this series is exactly 1. We argued this by doing the partial sums and calculating the limit, but it's also a special case of this general result. This general result that when you sum a geometric series, you get this very easy looking answer for the sum, right? So a divided by 1 minus r is what the sum of the geometric series is. Okay, and if you do this example where a is 1/2 and r is 1/2, then this expression simplifies to be 1. All right, any questions? Okay. Okay, so here's an application. So this is an application in finance. Okay, so this is something called a perpetual annuity. Okay, so suppose you can earn 5% interest per year by depositing your money in a bank. Okay, so the question is, so what's an annuity? An annuity is something that pays you a certain amount of money for in perpetuity, basically as long as you live at a certain time intervals. So the question is, how much should it cost to buy an annuity that pays you $100 a year from now, and then another $100 a year after that, and then another $100 a year after that, and so on for the rest of time? Okay, so this is a tough question. I claim the answer is going to have to do with geometric series. But let's look at it, right? So, well, the question is how much to pay now to get $100 in 1 year? How much would you have to pay now to get $100 in 1 year? Well, we've seen that in the bank, you can earn 5% interest per year, right? So if D equals money now, then D times 1.05, that's adding 5%, equals money in 1 year, right? So how much do we pay now to get $100 in 1 year? Well, we have this equation. D times 1.05 gives you the money in 1 year. So that means if you want $100 in 1 year, you solve D times 1.05 equals 100. Okay, and that tells you that, D is equal to 100 divided by 1.05. And I mean that's fine. Maybe we'll just leave it like that. Okay. Or if we want to think about it, if we don't like decimals, we can multiply by 100 over 100. So that's 10,000 divided by 105. This is how much you need. So how much do you pay now to get $100 in 1 year? The answer is this. You have to invest 100 divided by 1.05. Let me say what that is in decimals. So 100 divided by 1.05. So this is roughly $95.24.
Adobo?
Yes, Robert?
Yeah, I'm confused. How is it
Yep.
that the rate is 1.05?
Because you earn 5% interest. So if you have D now, then what do you get in a year? You still have your D that you started with. That's the one. But then you also get 0.05 times D. That's the interest. So when you add them together, you get one and then an extra 0.05 for interest.
Okay, I understand. Thank
Okay,
you.
makes sense? Okay, you're welcome. Okay. So basically, earning 5% interest a year means each year your money gets multiplied by 1.05. Okay. So if you put $95.24 in the bank today, then in a year you'll have $100. Okay. So let me do one more example. Right. So for D, let's say how much to pay now to get $100 in 2 years. If due to get $100 in 2 years. Well, if D equals money now, then D times 1.05 is equal to the amount of money in 1 year. And then D times 1.05 squared is equal to the amount of money in 2 years. Okay. Right? Each year you multiply by 1.05. That's getting 5% interest. It's getting an extra 0.05 on top of what you already have. So in order to solve this, we have to solve D times, so solve D times 1.05 squared equals 100. That's going to give you that D equals 100 divided by 1.05 squared. And if you do this out with a calculator, this turns out to be roughly $90.70. Okay. And so now we kind of see the pattern, right? In 1 year, to get $100 in 1 year, you need 100 over 1.05 to the 1. To get $100 in 2 years, you need 100 over 1.05 squared. And then we can see the pattern to get $100 in n years requires 100 divided by 1.05 to the n now. Okay. So if you want to get $100 in 10 years, then you need to do $100 divided by 1.05 to the 10th now. That's what's going to give you $100 in 10 years. Okay. So we still haven't answered the question. The question is, what does it cost to buy this annuity that doesn't give you $100 in 1 year or in 2 years or in 10 years, but it gives you $100 every year, right? You get 100 in 1 year, and then 100 in 2 years, and then another 100 in 3 years, and another 100 in 4 years, and so on, forever. Okay? Well, what happens? So let me do another page of this. So how much should it cost to buy the annuity? Well, it gives 100 in 1 year, and $100 in 2 years, and $100 in 3 years, and so on forever, right? So you should think of it as being the sum total of all of these payoffs, right? You get $100 in 1 year, you get $100 in 2 years, you get $100 in 3 years, and so on for the rest of time. Well, we know how much each of these costs, right? If you just wanted the 1 year payoff, this should cost 100 divided by 1.05 to the 1. If you just want the 2 year payoff, this costs 100 divided by 1.05 squared. If you just want the 3 year payoff, this should cost 100 divided by 1.05 cubed, and so on. So what this tells us is that the total annuity should cost, well, it should cost 100 divided by 1.05 to the 1, plus 100 divided by 1.05 squared, plus 100 divided by 1.05 cubed, plus 100 divided by 1.05 to the fourth. 1.05 to the fourth, and so on, as an infinite series, right? Because each one of these is the cost of one of the payouts. So if you want to get payoffs forever, it should cost the sum of all of these things. Maybe it's an annuity that stays in your family. Even after you die, you can get payoffs for your heirs. Okay. Well, how do we evaluate this sum? Well, this is a geometric series. Right? This is a geometric series. With the first element, the A is just 100 divided by 1.05. And what's the common ratio? Well, each entry, the denominator gets multiplied by 1.05, right? You have this. The next entry is the same thing with an extra 1.05 in the denominator, and then an extra 1 in the denominator. So our R here is 1 divided by 1.05, right? That's our common ratio, because to get from each entry to the next one, you have to multiply by 1.05. And this thing is less than 1, right? Because 1 is less than 1.05. So what do we get for the sum? Remember, we have our formula is A over 1 minus R. That's equal to 100 divided by 1.05 over 1 minus 1 divided by 1.05. Right? This is our A, and this is R. Maybe I'll multiply by 1.05 divided by 1.05 just to simplify the fraction. So this gives 100 divided by 1.05 minus 1. Right? I multiplied both the numerator and the denominator here by 1.05. Here, that just gets rid of the 1.05. Here, it gets rid of the 1.05, and it turns this 1 into a 1.05. So this simplifies to 100 divided by 0.05. And that simplifies, if you do it on the calculator, this becomes 2,000. Okay? So this is the answer here. If the bank will give you 5% and you want something that will give you $100 every year forever, then the fair cost of that is $2,000. That's how much you need to give upfront in order to be paid $100 per year for the rest of time. Okay, and the way you calculate this cost is by doing these geometric series. It's a geometric series of what each payment costs. Each payoff should cost this much. And so if you want all of the payoffs, you need to pay all of these prices up to infinity. And when you sum that up, it turns out with the geometric series, that gives you a sum of 2,000. Okay, so these geometric series allow you to actually, calculate a fair price for these kinds of financial instruments. Okay. All right. Any questions about this? Okay, so I want to give you an example. These geometric series is not just some sort of mathematical thing that we do for fun, but it actually really has applications. It has a lot of applications in economics, but it also has applications in physics and relativity and radioactivity, things like this, which I don't have time to talk about today. But what's nice is that you have this very simple formula, which allows you to add up these series, and these series turn out to actually have some meaning. Okay. So I'll put a $sign here. Okay. Okay. All right. Do we want to do telescoping series? Yeah, I guess we have time. Maybe I'll give one other example of a series that you can add up. So let's say that you want to add up the sum of this series. So this is, you can think, this is, 1/2 plus 1/6 plus 1/12. The next term is 1 over 4 times 5. So that would be 1 over 20. And then 1 over 5 times 6, 1 over 30, and so on. So suppose we want to add up this series. Well, so how do we do this? Well, of course, it's a series. We've got to do partial sums. That's the only thing you can do. So if you look at S1, this is going to be 1/2. S2 is 1/2 plus 1/6. This actually becomes 4/6, which becomes 2/3. S3 is 1/2 plus 1/6 plus 1/12. That's actually going to be 2/3 plus 1/12. If you do this in terms of 12th, this becomes 9/12, and this becomes 3/4. Maybe I'll do one more. So S4 is 1/2 plus 1/6 plus 1/12 plus 1/20. Well, we know this part over here is 3/4. We already did that. So that's equal to 3/4 plus 1/20. And if you get a common denominator and simplify this out, this becomes 16 over 20, and this becomes 4/5. So the pattern of partial sums here is, it looks like you have 1/2, then 2/3, then 3/4, then 4/5. If this pattern continues, we should have 5/6, 6/7, 7/8, and so on. Okay. And so what's the limit? So what's the limit of this sequence? 1/2, 2/3, 3/4, 4/5, 5/6, 6/7, 7/8. What is the limit going to?
Hello.
Yep. Abraham?
Yeah, it's going to 1.
Exactly. Great. So the limit's going to 1. And so that means the sum of this series is equal to 1. Okay, and so why is this called a telescoping series? Basically, why does this pattern work? So where, maybe I'll just ask where, so the answer is 1. So the sum of the series is 1. So if I ask, where does the pattern come from? Hey, well, what happens? Well, the point is 1 over 1 times 2. It turns out you can write this as 1 over 1 minus 1 over 2. And 1 over 2 times 3 is 1 over 2 minus 1 over 3. 1 over 3 times 4 is 1 over 3 minus 1 over 4. And 1 over 4 times 5 is 1 over 4 minus 1 over 5, etc. I'm going to leave this as an exercise to verify this. But the point is, if you do a common denominator for this, you're going to get 5 over 4 times 5 minus 4 over 4 times 5. That's going to give you 1 over 4 times 5. Okay, sorry, your battery's running low. We'll be done in about 10 minutes. Okay. Okay. So it turns out this is true. So when you're doing this series, what do you actually get? Well, this 1 over 1 times 2, you can write it so the series is you can write it as 1 over 1 minus 1 over 2. Then 1 over 2 times 3, that's going to be plus 1 over 2 minus 1 over 3. And then the 1 over 3 times 4 is 1 over 3 minus 1 over 4. And then the 1 over 4 times 5 is 1 over 4 minus 1 over 5. And now you kind of see what's happening. The minus 1/2 and the plus 1/2 cancel. The minus 1/3 and the plus 1/3 cancel. The minus 1/4 and the plus 1/4 cancel. The minus 1/5 is going to cancel out with minus 1/5 later on. And you see that the only thing that doesn't cancel is exactly this first term. This 1 over 1 doesn't cancel at all. And everything else cancels. And so that means that the sum of everything ends up just being 1, which is exactly what we figured out over here. Okay.
Oh,
Yep.
Robert?
Yes, question.
Yeah, so the first term of this series is 1 over 1, right?
Exactly. Well, no, the first term in the series is really 1 over 1. It's really 1/2, but I'm rewriting that 1/2 as 1 over 1 minus 1 over 2. So that when we see all of these terms in the series, 1 over 1/2, 1 over 2, 1 over 6, 1 over 12, I'm rewriting them as 1 minus 1/2, and then 1/2 minus 1/3, then 1/3 minus 1/4, and then 1/4 minus 1/5. So when you write them out like this, I'm putting them in parentheses because each parentheses is one part of the series. But when you write them out like this, you see where all the canceling comes from. And so now you see why the limit is 1, because really it just comes from everything canceling except for this first part of the first term, which is 1.
Okay.
Okay. Okay, other questions?
What happened?
Yes, Robert.
So why is it called a telescoping series?
The telescoping, I don't, a telescope, you think of it as it has a lot of parts that fold into each other. And so you think of these parts, I guess, as folding into each other. When you have lots and lots of cancellation, that's kind of like taking a telescope and pushing it together. You have all of these parts that cancel out with each other and shrink it. I mean, it's it's an imperfect metaphor. But I think that's why. The point is you have this long series and it shrinks into just the first element, and that's kind of supposed to remind you of compressing a telescope.
I see. So it means that if I take this series and try to pull it into GeoGebra and look at the diagram, one will look at the telescope.
Right. Yeah, no, it's not. I mean, the telescope is just a metaphor for canceling all of these terms. Anytime in math that you have a lot of cancellation, you call that telescoping. You have a lot of plus
Okay.
and minus of the same thing, then you call it telescoping.
All right. Thank you.
Okay, you're welcome. Okay, other questions? Okay. Okay, so last slide before the homework. So here's some more mysterious series. Okay, so here are all facts. I'm not going to explain any of them today. But it turns out that if I take 1 minus 1/3 plus 1/5 minus 1/7 and so on, that actually converges to pi over 4. Seems a little crazy, right? And if I take 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 and so on, that actually converges to the natural log of 2. And if I take 1 plus 1/4 plus 1/9 plus 1/16, I put all of the square numbers in the denominators, so plus 1/25 plus 1/36, etc. that actually sums up to pi squared over 6. Okay, so these are all crazy, right? I mean, it's one thing to say that, 1/2 plus a fourth plus an eighth plus a 16th and so on equals 1. That's a geometric series. I mean, it was creative to figure out how it works, but it maybe wasn't that surprising. We could kind of explain it by drawing a picture. These are nuts, right? I mean, the idea that any of this could be true is incredible. Okay, that you get pi and natural logs and everything just from simple fractions on the left-hand side. Okay, but these are all true. And so the question is, how could you ever deduce something like this? And next week, well, at least for the first two. So the third one is beyond the scope of the course. The third one is going to be too hard for us to talk about. But these first two, I'm not going to give a full proof, but I'm going to try to give an overview of why you can expect something like these first two series to be true. And what this uses is what's called Maclaurin series. And so Maclaurin series actually give you these full identities. So a Maclaurin series actually gives you something that's much more than just these two series. So Maclaurin series tells you that for any x, at least between -1 and 1, if you take x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so on, that actually always gives you inverse tangent of x. And if you take x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, that's actually always going to give you the natural log of 1 plus x. So what happens when we plug in 1 to these series? So if we plug in 1, this tells us that 1 minus 1/3, or 1 cubed over 3, plus 1 to the 5th over 5, minus 1 to the 7th over 7, etc., that this is equal to tangent inverse of 1. Well, all of the powers of 1 are just 1, so this is just 1 minus 1 over 3 plus 1 over 5 minus 1 over 7, etc. And this is tangent inverse of 1, so we're asking what angle gives you tangent that's equal to 1? Well, that angle is 45 degrees, if you remember your trig tables. So if you remember that tangent of 45 degrees is equal to 1, or in radians, 45 degrees is the same as pi over 4. Tangent of pi over 4 equals 1. So that tells us that tangent inverse of 1 is pi over 4. Okay, so this is where we get the first series from, over here. You get this general equality of functions, and then when you plug in x equals 1, it ends up giving you this series. And similarly over here, if you have this series of functions, maybe I won't write it down, but you can just see. If I plug in 1, here I get 1 minus a half plus a third minus a fourth plus a fifth minus a sixth, so on. And on this side, I have ln of 1 plus 1. So that's ln of 2. Okay, so if you plug in n equals 1 here, if I punch in x equals 1 here, then that gives me the second series. Okay, third series is not quite as easy. I'm not really going to be able to talk about it. But the third series was discovered by Euler in the 1700s. Okay, he was the one who showed that this was true. Okay, so these are a little more mysterious. We'll spend the last week telling you what so-called Maclaurin series is, writing a function as a series, and showing how that gives us these very kind of surprising series identities over here. Okay, so this is a preview for next week. Okay, homework for this week is more basic. So the first one is to evaluate the sum of the following geometric series. This is the one from the beginning of class today. So 18 plus 12 plus 8 plus 16 thirds plus 32 ninths. And so can you evaluate the sum of this geometric series? Second question is, I take this kind of weird series, 1 minus 1 plus 1 minus 1 plus 1 minus 1. And I'm asking you, does this diverge or does it converge? And I want you to justify it. So can you add up all of these numbers or not? Okay. And then the third question is a little bit more involved, so I just want to draw a picture of it. So start with the interval 0 to 1. So here's the interval 0 to 1. So here's 0 and here's 1. So then what I'm going to do is I'm going to remove the middle 1/3 of it. So I remove the interval 1/3 to 2/3. So what I'm going to do is I'm going to erase the middle 1/3 of this interval. Hold on, let's call it this. Okay, so I'm going to erase the middle 1/3 of this. So this would be 1/3 and this would be 2/3. Now I'm going to look at each of these and I'm going to remove the middle 1/3 of each of these segments that remain. So I have to remove the middle 1/3 here, and I'm going to remove the middle 1/3 here. That actually gives me 1/9, and then 2/9, and this is going to be 7/9, and this is going to be 8/9. And then we keep doing this. So now I remove the middle 1/3 of each of these segments, which I won't try to draw because it's too small. And then I remove the middle 1/3 of all of that, and you keep doing that forever. So it turns out that the points that remain is called the Cantor set, after you keep removing the middle 1/3 of every interval that you see. So this question is a challenge, by the way. Okay, challenge. So the question is, how much total length has been removed at the end? And my hint is that this can be figured out by evaluating the sum of a geometric series. So think about how much you're removing at each step and add that all together. That's going to be a geometric series. And so then the question is, once you figure that out, then what is the total length of the Cantor set? Okay, the Cantor set is everything that's left after you remove all of these intervals. Okay, so this is a challenging question. We'll spend a little bit of time talking about it next time. Okay. Okay, so next time, so thank you again for your attention. So next week on May 29th will be the last session of the academic year, and we're going to talk about Taylor and Maclaurin series, and this is a technique that allows us to write common functions as series. Okay, and that's what allows us to get these series like ln of 1 plus x equals x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 and so on. Or that tan inverse of x gives you x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 and so on. And this topic's going to bring everything full circle because these Taylor and Maclaurin series are going to end up being based on calculus and derivatives. So we're going to be going back, integrating the series with the calculus, and it'll be a good way to close the year, to close up the curriculum for the year. Okay, so all right, so thank you as always for your attention. I'll give you one last chance to write your name if you haven't done that already, and then I'll turn off the recording. And as always, I'll send out the notes and I'll send out a link to YouTube. Okay, so I'm going to turn off the recording now. So last chance to write your name if you haven't done that.